Today we will go over section 6.8, which is linear combinations and spanning sets. Now, we will first start by examining linear combinations of vectors in 2 dimensions. I will define what linear combination is with an example because it makes it way easier. So let's say I have the A value, A vector, which is right over here. It's this tall, it cuts right over here. And the coordinates for that is -1 and 2. And I also have a B vector, which is right over here, and the coordinates for that is 1 and 4. Now, I can put any scalar, I can multiply by any scalar for those vectors to get a different value, like we did before. So let's say I was to multiply A by a value of 2. What is that going to make in terms of my A vector is, my A vector is this small, okay? And when I multiply by 2, then I lengthen. It just gets longer. And that would be my 2A. And let's say I was to multiply B by the scalar 3, then it would be this line right over here and -3. So it would be in the opposite vector and it would just be longer. And as a result, I would get a coordinate of -5 and -8. What we call the linear combination is this portion. So linear combination, I'm just going to say LC, is just an expression and it's constructed from set of terms by multiplying each term, so each value, each coordinate over here, by a constant and adding the results. If you look at the definition given by the textbook, it might be a little confusing on what it's trying to say, but bear with me. For non-collinear vectors, which I'll get a little bit later on and explain why it cannot be a collinear vector. So let's just skip that for now. U and V vectors, so in this case this would be A and B vectors. So these are the vectors. A linear combination of these vectors is AU plus BV, where A, B are scalars. So those A and B would be represented by 2 and -3. So this is only in the form of -2 and then A vector, as well as -3 and a B vector, right? Then this is a linear combination. The vector AU plus BV, the vector, the result we get for that vector is the diagonal of the parallelogram formed by the vectors AU and BV. And this can be proven by the graph right over here. Let me erase it a little bit. But when you look at the vector, the resultant vector, it is diagonal to my parallelogram. If you look at the parallelogram itself, it's located right over here. So this is my parallelogram and it runs diagonal to it. So that's also another way we can differentiate it. So it will make more sense with an example. Show that x equals 4 and 23, that's the coordinates, and can be written as a linear combination of either set of vectors -1, 4 and 2, 5, or 1, 0 and -2 and 1. So in this question, what's given to me is set 1. I'll just differentiate it. Set 1 is this. So it's saying make sure this equals to my x vector, or show that this set equals to this. So to actually make a linear combination, like I told you guys, it needs to be in a format where I have a scalar multiplied by it, right? So that's what I'm going to do. I saw before that if I multiply the coordinate by a scalar, let's say I'm just going to say A in this point, and it's multiplied by -1 and 4. And if I add that, so combine that with the other coordinates given to me, which is 2 and 5, but that also needs to be multiplied by a scalar given to me. So I'm just going to say B because I don't know the scalars, okay? So over here, now I have 2 and 5. And I know this linear combination is going to equal to whatever is given to me, which is 4 and 23. Now what I'm going to do is I'm going to distribute the scalar into my bracket. So I will be getting -A, 4A, and then I'm also going to distribute the B inside the bracket, which will give me 2B and 5B. And this will equal to 4 and 23. Now all I need to do in order to add these is add the x's together so x values, and add my y values together to get x and y format. So when I do that, I'm going to get negative a plus 2b, and for my y values, I'm going to get 4a plus 5b. And this will equal to my value 423. Now I can actually make two equations from this. I can take this one and equal, because I know this is the x coordinate, which will equal to 4. So I can say negative a plus 2b will equal to 4. And I can take this y coordinate and equal it to 23 over here. So I will have 4a plus 5b equaling to 23. Now from what I have two unknown variables. I can eliminate one of them and find the other. So to eliminate them, the easiest way I'm thinking of right now is multiplying this by 4, which will give me negative 4a plus 8b equaling to 16. And I have the same thing. I didn't do anything to the bottom, so that stays the same. Now I see I have a negative 4a and a plus 4a, which can cancel out. Now as a result, I'm going to put it right over here. I add all these, so adding 8 and 5 will give me 13b equaling to 39. Now I'm going to divide each side by 13 to get a value of 3. So I found my b. The only thing I need to find is what is my a value. So I can just plug in that b back into my original equation, which is easier. So I have negative a plus 2, and then I'm going to plug in 3 for that. And that equals to 4. I know 2 times 3 is just 6, so I have negative a plus 6 equaling to 4. I'm going to send that 6 as negative to the other side to get a value of negative a equaling to negative 2. Divide by negative for each side, I get a value of 2 for my a. Now that I got my first linear combination, the next set I need to do is the given one right over here. So I'm going to do the same thing for that one. I don't know a scalar, what's the scalar in front of it, right? So in this case, I'm just going to use for, not to confuse the letters, I'm going to use C and D for the scalars I'm going to do. So I will be saying a scalar C will be multiplied by the coordinate 1 and 0, plus, and a scalar D would be multiplied by negative 2 and 1. And I know this will equal to 4 and 23. Again, the next thing I'm going to do is distribute these scalars into the brackets. So when I do that, I'm going to get C, and because it's 0, it's just going to be 0 for this one. I'm going to say plus negative 2D and D for this one, and it will equal to 4 and 23. From here, what I'm going to do is I'm going to put the x's together, and I'm going to put y values together. When I do that, I'm going to get a value of C minus 2D and D equaling to 4 and 23. Now the easiest one, I don't even need to make the equations up right now. I can do it just for the visualization purposes, but right now for the equations, what I have is C minus 2D, which represent my x, and I know this is my x value, so it will be equal to 4. And I know since this represents my y, D equals 23. But I already found one of my scalars, so I don't need any elimination process whatsoever. I can directly plug this into my first equation to find the value of C. So when I do that, I have C minus 2, and I know D value is 23, which will equal to 4. I know this is going to be C minus 46 equaling to 4. Send that 46 as a positive to the other side. I have C value equaling to 50. Now these would be my answers in terms of finding the linear combinations for each set. Now passing on to spanning sets, this might be a little confusing for some people, but it's actually really easy. It's just a textbook is like using fancy words to explain it, right? So I know my I, the unit vector I, represents the x coordinates, right, and goes like this, and it has a magnitude of 1. So this is my I, and I know J represents my y, and also has a magnitude because they're both the unit vectors, right? With linear combinations, what we learned is I can multiply these by any scalar to switch this j from, let's say, like lengthen it and make 2j, right? I can make it 5j, I can make it longer. Same thing with I can multiply by even like -2. When I do that, I'll get a -2i value whatsoever. I can get any values, and when I add these together, which is a linear combination with the scalar, so let's say -2i, and I added it with the, I wrote it really bad, but let me just like do 3i, right? When I add these together as a linear combination, what I would get is a vector like this, right? When you add them together, imagine switching this 3i to right over here, then that would be a 3i, and you would get that vector. So just like this, you can literally get any vector by using the linear combination. I can just use I with a 3i, then I'll get a vector over here. I'll do -3j. This is not I, by the way, this is j. So I'll do -3j over here, and I'll get a vector like that. So you can really span anywhere on the xy plane. So that's what it means by the set of vectors ij, which is the unit vectors that I said over here, is set to form a spanning set for R squared, which is the xy plane. Every vector in R squared can be written uniquely as a linear combination of these two vectors. What it means is you can really have multiple linear combinations, and it will be spanning. Spanning meaning it's not really like spanning, but it will have, you can really have it anywhere, right? You can have it here, you can have it depends on what the scalar is. So when it also says any pair of non-zero and non-collinear, which I said I will get back to it, it's like that won't be really spanning the R squared, is because if you have a non-zero, so let's say this is your xy plane, right? And let's say my pair is 0. My pair is 0, meaning let's say one of the pairs is 0, which would be located right over here. So one of the pairs is 0 and 0, and the other pair is also 0 and 0, and it will be right over here. Then you're stuck at the origin. You're not creating any vectors whatsoever. It's not really spanning anywhere. You're just stuck at the origin. So that's why it has to be a non-zero value. Same thing with the non-collinear. So let's say I have a set like this, and the other one is like this, right? Whatever you do, it will just be either over here, either over here, either over here, right? It won't be really anywhere else. You're stuck with that collinear vector for R squared. So only thing for R cube is that instead of saying any pair of non-zero non-collinear vectors will span R squared, they just add it will span a plane because it's three-dimensional. So let's say I had this value, and I had this value, and I had this value. When I actually add them together, I would get something like this. So I will add the green portion to the end of the where the x coordinate is. So I will rewrite this, and I will also put the y one onto here. So now if you look at here, what you have is not just a vector, it's a plane. So I know my vector will span a plane in R cube, so it can be within here. So that's why it says a plane in R cube. So let's try an example on spanning sets. It says show that the set of vectors given to me is a spanning set for R squared. In order to do that, first I need to set my linear combination, which we learned how to do before. So I just need to put a scalar. So I'll just put a and b over here, which I don't know the scalar for, right? So I'll just say a and 2 and 1 plus the b and -3, -1. And you might be saying, well, what does that equal to? It will equal to any x and y coordinates on R squared. So that's just going to be, because it says R squared, I only have x and y, I don't have z. So it's just going to be equal to x and y. From here, I can just distribute the a like we did. So I have 2a, a plus -3b and -b. right? And this will equal to x and y again. From here, I can add the x's together and I can add the y's together. So when I do that, I actually get 2a minus 3b, a minus b, and this will equal to x and y. And like we did before, I can get two equations from this. First, I will start with the x value, so equaling x values together. So that would give me 2a minus 3b equaling to x. And same thing over here, this is a y value, so a minus b will equal to y. Now, what I'm trying to find is what are the values for a and b, right? Even though you might be saying like we don't know what x and y is, but we need to find the scalars of what a and b is first in terms of x and y. To do that, the easiest way is to eliminate one of them. So what I'm going to do is I'm going to multiply this by -2. So when I do that, I get a value of 2a minus 3b, so the first one just stays the same. The second one, I say -2a plus 2b equaling to -2y. And adding them together will just eliminate the a's. Over here, I only have minus b left, and over here, I'm left with x minus 2y. Sending that negative to the other side, I would get a value for b equaling to -x plus 2y. Now that I have my b, all I need to do is plug that back into my original equation, which I see that the easiest one is over here. So I'm just going to say a minus whatever I found for b, which is -x plus 2y, and that will equal to y. Now from here, I'm going to distribute that negative to inside the brackets to get rid of their brackets. So I have a plus x minus 2y equaling to y. Send everything to the other side, so I'm left with a. So right now I'm left with y minus x plus 2y, which I can add these y's together to get a value of a equaling to -x plus 3y. Now, what I need to do is I have the equation for a and b, but I don't know the values of a and b. And because it says it's spanning set for r squared, this technically means whenever we are giving like the components of any vector, we can find the corresponding values for a and b. So let's say you were to say my xy value that we set equal to, which is here, is, let's say, 3 and -7, right? So -3 and 7. Let's say -3 and 7. From here, what I can do is I can plug in the x and y. So let's say this is my x and this is my y, right? I can plug in those values into a and b, find a value and make it equal to that. And if that works out, it is spanning. So as for my a value, I'm going to get -3 plus 3 and 7. As for my b value, I'm going to get -3 again, but then plus 2, 7, right? So as for my a value, I'm going to get a value of 24, and as for my b value, I'm going to get a value of 17. Now all I need to do is plug in these values in the place of a and b, which when I said a over here, this will become now 24. And as for my b value, this will become 17. And as for my x and y's, it will just become -3 and 7, which I plugged it in. So I'm just going to say that it would be -3 and 7. So I can say yes, the set of vectors, they are spanning set for r squared. So let's say this time we need to show that set of vectors does not span r squared. So how do we differentiate that? We will apply the same process. So I'm just going to put the scalars a and b in front of it. So now I'll have a 2, 3 plus the b 4, 6, right? And this will equal to any coordinates on my r squared. Now I'm going to distribute the a into the brackets. So I have 2a, 3a, and a plus 4b, 6b, and that equaling to x and y. Now I need to put the x's together, and I need to put the y's together. When I do that, I'm going to get 2a plus 4b, and 3a plus 6b, and this will equal to x and y. Now from here, all I need to do is put this x coordinate equal to my x, so I have 2a plus 4b equaling to x. Now from here I have y, which equals to y, so I'm just going to say 3a plus 6b equaling to y. The thing to realize is that this has a common number which I can take out, which is 2. I can divide this by 2. If I divide that, what I get is actually, before doing this, what I get is actually a plus 2b, right? This is 4x, so I'm just going to apply. I'm just going to say this is for my x coordinate. Now for this one, what I realize is I also have a common factor I can take out, which is 3. So if I divide that by 3, I'm going to get a plus 2b, which represents my y. And I see that these two equations are actually equal to each other. They're the same thing. So this actually shows my lines are collinear. And remember how for the spanning sets they said it cannot be collinear, or it just cannot be 0. So that way I can just be like, this does not span R squared. Now the very last question is, given the two vectors over here, which is a and b, does the vector c lie on the plane determined by a and b vectors? And we need to explain why. So all this is asking for is, for the linear combinations by a and b, right, will this be equal to c? Meaning, will c be on the plane determined by this linear combination? So all I need to do is, again, I'll put a scalar. For this one, I'll just say d and e, not to confuse with the vectors. So for the part a, I'm going to say d, -1, -2, 1, and let's say e for this, right? E, so plus e, 3, -1, and 1, and I know this will equal to -9, -4, and 1. All I need to do is distribute. When I do that, I'm going to get -d, -2d, and d. And from here, I'm going to get 3e, -e, and e. And this will equal to, again, -9, -4, and 1. Now from here, I'm going to put the x's together, right? I'm going to put y's together, and I'm going to put the z-axis together as well. So what's different about this question is, now it's r cubed, not r squared. So now here, what I have is -d plus 3e, -2d minus e, and d plus e. And this will equal to -9, -4, and 1. Now I can make 3 equations from this instead of 2 equations now, because I know this represents x and my x is -9. So I can say -d plus 3e will equal to -9. Now this represents my y, which will be -2d minus e will equal to -4. And the last portion is the z portion, which is d plus e equaling to 1. Now, easiest way to deal with this question is, instead of using it all, because whenever you have 3 equations, you don't use it all, I'm going to number these. So my equation 1, equation 2, and equation 3. And what I'm going to use to eliminate is equation 1 and 3. So I'm going to use -d plus 3e equaling to -9. And I'm going to use d plus e equaling to 1. Because why I use those two specifically is I can directly cancel the d's out, because one of them is negative, one of them is positive, and all I need to do is add them. So I'm going to add 4e, and that would equal to -8. Divide each side by 4, I'm going to get a value of -2 for my e value. Now that I have my e, all I need to do is plug into my equation. The easiest way is, let's use the equation 3 and plug it in to find the d value. So I'm going to have d minus 2 equaling to 1. Therefore, my d value will equal to 3. Now all I need to do is plug these values back into my linear combination. So instead of saying D, I'm going to say now 3 over here. And instead of saying E, now this is going to be -2. So remove that plus sign as well. So -2. So for my question, I can say yes, it does lie on that plane. So the part B is saying, does the vector lie in the plane determined by the first two vectors? Now, even though I said, oh, it lies on the plane, we need to check if it actually does, and which is why it's the second part of the problem. So by just looking at it, you can be like, yes. So but we found the equation like that, and we said D will equal to my 3 and E will equal to -2. All I need to do is check if it actually equals these values, because these values at the end represent my C, which will say, okay, this does actually lie on the plane determined by these A and B vectors. So I'll start with the first one. The first one is -3 plus 3 and then -2 when you plug it in, which needs to be equal to -9. So from here I have -3, -6 will equal to -9. And in fact, -9 will equal to -9. This is right. But you cannot just stop there. You need to check the other ones. Now, let's say for the second equation, my D value is 3, and then it needs to be -2 equaling to 4. Now I have 6 minus 2 equaling to 4. And I know this is going to be 4 equaling to 4. However, the vector they want us to check has a different y value, which is -5. This does not equal to -5, right? Equals to -9 equals to 1, but it does not equal to 4. So we can just directly say no, not for that vector. It just does not equal on the plane. Another thing we can check for this one though, it does equal to 4, it does equal to 1 if you want to check it over. So it does lie on the same plane for this one, but in terms of this one, because it's not the same, I cannot just say it lies on the plane because it does not equal to -5. So that's it for the questions you will see. If you have any questions or problems that you would like us to solve so we can send you solutions, you can always go to our website and go to the forum section where you can ask your questions.